Hi, my name is Malachi Nichols from ASU, and I'll be talking about photomask manufacturing for semiconductor materials, processing, and microfabrication. I'll be talking about today about what is a photomask and the three major types of photomask, the materials to make a basic photomask, the processing of one of the types of photomask, the modeling of one of those processes, the evaluation of defects in the photomask process, and the repair of said defects. Now, what is a photomask? A photomask is a stencil of an integrated circuit, and it's used in photolithography to transfer a pattern onto a substrate. That pattern being the integrated circuit and the substrate typically being silicone. Now, there's three main types of photomask, and the first type is the contact photomask, the oldest of the bunch, and it was physically put onto the substrate where then photolithography was performed, and because of this, it had really low durability. Now, to push for increased durability, they made projection photomask, which can then be projected through at a distance, and contact and projection photomask were both transparent with chrome on it to absorb some of the rays. Now, the newest type of photomask is the extreme ultraviolet photomask, which is a complete redesign of the photomask because instead of being transparent and absorbing some of the rays, it's reflective, and it reflects these rays to get an even smaller area. Now, in a basic photomask, there are three main materials used. The first one being glass or fused silica substrate. This is the bottom of the photomask and the baseline. The second material is chrome, which tends to be either chromium or iron, the part that absorbs the rays. And the third and most recent addition, not 100% necessary, however, has become a absolute need in the process of reducing defects, is the pellicle, which tends to be made out of plastic polymers. Now, the process of photomask. I'll be talking about the processing of a projection photomask from its blank all the way to its finished photomask. Now, step 0, we have to talk about the blank itself. The blank is made out of three main components. First, we have the quartz or glass, the chrome on top, and the resist. The resist varies quite a bit, however, it will not end up on our finished product. Now, the first step in this process is patterning. Patterning typically can be done by two main machines, electron beam mask writers and laser mask writers. Here below is a mask writer. It is an electron beam mask writer by New Flare Technologies. Now, in patterning, we start off with our blank. And then we have our electron beam or laser come down and charge some of our resist. Now, this goes on to step 2, where it's development and etching. Now, the first part of this is going to be removing the resist, and then we're going to be removing the chrome. Now, below is a spin mask by APNS, which is a machine capable of developing the resist. Now, here's the development part of the process right here, where we develop that charged part of the resist away. And then that underlying chrome is available to then etch away, while the part below the resist cannot be etched away. And that's what our etching is. We're going to be removing that part of the chrome. That moves us on to step 3, the cleaning and adding of the pellicle. Now, there's two types of cleaning, wet and dry cleaning. And I talked about it a little bit earlier, but why a pellicle? A pellicle isn't necessary. However, it greatly reduces the defects because any particles that end up on the photomask end up on the pellicle instead. Now, here is a cleaning system, the 193i EUVL Photomask Cleaning System by SUSS Microtechnology SE. Now, here we have a representation of the cleaning process. So the cleaning process is essentially just going to remove that excess resist that we don't want. Now afterwards, we're going to add that pellicle to protect that chrome. It's going to provide us that shield. Now, I'm going to be talking about a model here, and this model is the electron beam proximity effects in mask writing. And this model is made by Paul J.M. and Chris K. Kloss. And it's shown in the Handbook of Photomask Manufacturing Technology in Chapter 2, page 52. And here's an example of a machine that this model could be used on, the JBX 3200 MVS electron beam lithography system by JEOL Ltd. Now, this model takes into account when electrons hit the resist from the electron beam, they scatter because of the electron's high kinetic energy. And the distance this electron can go to from its point of entrance is related to its kinetic energy, which is a function of the acceleration voltage. Now, below is the model, which is a weighted sum of two Gaussian functions. Now, in this model, the first Gaussian curve is the forward scattering electrons, the electrons that are going deeper into the substrate, or in this case, the resist. And the other curve is for the back scattering electrons, the electrons that are going backwards. Now, they are weighted between each other with a weighting factor of n, which is a ratio between the two curves. Now here's a picture of why we want these two curves, the two Gaussian curves. Here we have a 50 kilovolt and a 100 kilovolt data, and we see these lines are completely different between the electron density and the scatter range micron. By having the forward and back scattering capability in this model, we can model both of them with this one model. Next, we need to talk about the evaluation and repair. Now, why do we want to evaluate and why do we want to repair? Photomask, any defects that appear on a photomask will propagate onto future substrates that it is copied over to. And it is very important to get rid of all of those defects. And nothing's perfect, which is why we need to evaluate. We need to find these defects and then repair said defects. Here is the Matrix X800 Light series by Lastech, which can evaluate. And here's the NM6 by Brunker, which is a machine capable of repairing some of these defects. Now, here's some of the types of defects. There are many types of defects, and here's just 3 of them. Now, the first one is the pinhole. It's a deep hole, and a pinhole can be devastating. It can cause gaps or bridges to occur. However, a lot of times a pinhole can just be ignored. Really depends on the situation. Next, we have the chrome bridge. Here we can see it's almost like a hairline. Now, a chrome bridge needs to be removed, and it is capable of being removed. Now, this last defect is not something you can fix, and generally is a killer, the glass bubble, and it appears in the quartz. Generally, you would evaluate your quartz, and if you find any glass bubbles, you can't use that quartz. You just have to toss it out. Now, there's 2 main inspection methods. The first one is dye to database, where we're going to be checking our new photomask against a database of what that photomask should look like. And now the next one is dye to dye. We're going to be checking the original mask used to create the new mask and the new mask itself. The main difference between these two is that in dye to dye, any errors on the previous dye will propagate over to the next dye and won't be picked up by the evaluation because they are the same, because they both have the same and be compared to each other. Moving on to repair. Now, I'm going to be talking about 2 types of repair. The first type is laser defect repair. How? The laser defect repair evaporates excess chrome from the substrate, and it does have some disadvantages. It can splatter. Splattering is basically, instead of evaporating, it almost explodes. And this explosion puts the chrome everywhere, and that's not good. That can ruin it. And also, a lot of defects end up being too small for laser defect repair to work. And the last disadvantage about laser defect repair is that it can damage whatever you are working on. It's not perfect. It can damage whatever chrome you're working on, and that's not good. Now, the second type of repair I'm going to be talking about is the atomic force microscope nanomachining. Now, what is an atomic force microscope? It's basically a vibrating sharp tip with a laser that bounces off of it to measure height. And the vibration frequency, it changes due to interactions of atomic forces as the tip gets close to the surface. So that vibration frequency changes ever so slightly and can be used to measure the heights. And in this case, it's actually going to make direct contact with the photomask so it can abrade it away. And this does two in one by not only abrading away the defect, it also measures the defects. Now, it does have some disadvantages. It is very low throughput, and that bigger defects can take a long time to clear, and that it's only destructive. It's not additive. You can't add anything by abrading it away. And here's an example of the photomask being abraded by the atomic force microscope. Now, just to recap, we talked about the three different types of photomask: contact, projection, and the extreme ultraviolet. We also talked about the materials in a basic photomask, which is glass diffused silicone, chromium, and a pellicle, which is made out of plastic or polymers. Next, we talked about the processing of a projection photomask from blank to photomask, from the blank patterning, development and etching, and cleaning and adding of the pellicle. Next, we talked about the modeling of the electron beam proximity effect in mask writing. Next, we talked about the evaluation of defects, and we also talked about the pinhole, chrome bridge, and glass bubble defects. We also talked about the two inspection methods of die to database and die to die. We also talked about two different repair methods of the laser defect repair and the atomic force microscope nanomachining. Thank you very much. My name is Malachi. Have a good day.